Friends, this is going to be a quick video on identifying conic sections by their equations. So we already took a look at how to identify conic sections based on the type of angle on which the plane is cutting the cones. But now we're going to take a look at how, if we're just given the equation, how do I know? Am I dealing with a parabola? Am I dealing with a hyperbola, an ellipse, or a circle? Okay. So conic sections all come in the same basic standard form or generalized form, where we have ax squared, where a is a coefficient, a number of some sort. So ax squared plus a b value multiplied by x and y. Then a c value times y to the second power plus d times x plus e times y plus f is equal to 0. Okay? So I want you to be able to see an equation in some form with numbers, of course, throughout here, and just to have a general understanding of what kind of equation am I dealing with, what in general is this going to look like, how do I even move forward with it. Okay? For this course that we're working in now, we're only going to deal with the x squared quadratic term and the y squared quadratic term. This second degree term, of course, because it's x to the first and y to the first, it's also a second degree term, but we're not going to worry about that right now. You'll have plenty of time to worry about it in the future. I'm not worried about that. Okay? All right, so let's take a look at how these equations actually line up with the different shapes that we know. So we've got parabolas, and we all know that parabolas are these sort of U-shaped curves that happen when we cut the plane at the same angle as the side of the cone. So generally, you've seen equations of parabolas in the form y equals ax squared plus bx plus c, where you've usually got it solved with y on one side, and you've got an x squared term. You might have a linear term, or that might be omitted, and you might have a constant term. What that means for a general formula is that there is this second quadratic or second squared term missing, right, where c is equal to 0. So it's not even there at all. So what we've got is only one squared or quadratic term, and then we've got potential for a linear term. This y term is usually solved on the other side, right? It's usually moved over to the other side, so it's solved for that y, and then we'll have a constant. So you should be able to identify or recognize when you have a parabola. The only difference will be that sometimes they'll leave this y value, right, on the left-hand side while solved for 0. So you should just be aware of that. Of course, it is possible that you could have a sideways parabola, right? And even though this isn't a function, as we know, because it fails the vertical line test, it's still a curve, right? And it's still a conic section. But in this case, instead of not having the y squared term, we now just don't have the x squared term. That a is equal to 0, so that's gone. And we've solved instead for x. So we might have a curve like this, like x equals y squared plus 2. Okay? But generally speaking, in a parabola, there's only one quadratic term. Okay, so just count, right? How many quadratic terms? Oh, there's only one squared here. There's only one squared here. So those are parabolas. Okay. Now, it is totally possible that you've got ax squared and a cy squared in your equation. Okay. And so then the next thing you want to check is the signs, right? So if the signs are different, right, here we have a positive ax squared minus, so a negative cy squared. If those signs are different, then we're dealing with a hyperbola. That's all it takes to make this hyperbola shape identifiable in the equation. Okay. Of course, we could have a negative ax squared and a positive cy squared, in which case we'll have a hyperbola oriented in the other direction here. Okay. In an ellipse, we have both an x squared term and a y squared term, but the signs are the same. Okay, so they are either both positive, or so we have a positive a and a positive c, or we could have a negative a and a negative c case. So the signs are the same for any type of ellipse, and a circle I'm sort of counting as a subsection of ellipse here. Okay, so the signs need to be the same for a circle as well. But if it's a smooshed ellipse, right, like here, then our a value and our c value will not be the same. Okay, so here you can kind of think about it, right? Here we're stretched in different degrees in different directions, right? So we've got different coefficients for x and y. In a circle, though, we're not stretched any differently vertically than we are horizontally, so our coefficients for a, for the x squared, right, the ax squared and the cy squared terms are going to be the same. So the circle has same a terms and c terms. So that should be enough to identify, just looking at an equation, what type of conic section am I dealing with. So just to recap really quickly, if we are trying to figure out what kind of conic section is my equation, step one, check for powers of 2. If there's only an x squared or a y squared and not both of them together, then you're dealing with a parabola. If you have both an x squared term and a y squared term, check the signs, because if they're different, it has to be a hyperbola. So then you're done. If they're the same, then you need, if the signs are the same, right? If you have a positive x squared and a positive y squared, or a negative x squared and a negative y squared terms, then you still need to check the values for a and c. Because if the coefficients are different values, you've got an ellipse, but if the coefficients are the same, you have a circle. Okay, I hope that helps you go ahead and identify these equations when you see them, so that you know which direction to move forward with them. Thanks.